And she said, we take it personally for our company and the country.
So that kind of exposes what happened to Moore's Law, what happened to the end of Moore's Law.
Researchers at Los Alamos National Lab put out a paper in which they're claiming they've pretty major breakthrough on quantum machine learning.
So UCI is a really big deal, a ripple effect across the industry.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hey Shaheen, good to be with you again.
Hello, lots been happening.
Yeah, I think the biggest event of the week was the Hot Chips conference. And, with our increasingly tech-driven world, what they talked about at this conference, which I guess has really taken off as a conference in terms of attendees, and you were one of them, but it's really become a prominent annual event.
It really has. I started attending 4 or 5 years ago. It was, of course, in person at that time, always held on the Stanford University campus. So it's down the street from where I am. It's convenient. And I think it was maybe a few hundred people. When it went online, obviously the number of attendees increased because it can now be global, and it is. But this time they had 1,700 registrations as of the first day of the conference.
Yeah, that's amazing. Now, a highlight of the event was a big presentation from Intel's CEO, Pat Gelsinger, who, to remind our listeners, returned to Intel and took over that post early last year, I think in February. And he's really been trying to revive Intel as chip leader, not only in design, but in fabrication. He's definitely invoking the revival of interest, or trying to revive interest in Moore's Law through this whole notion of assembling systems from multiple chiplets. So stacking chips, as we were talking about last week, into more than systems on a chip. I guess that's the old phrase. The new one is SOP, system on package.
When SoC came about, many of us thought that that when you say system on a chip, you really meant an actual entire server on a chip. But we are finally approaching that, where you really can get substantially most of a computer on a single package now, because they're right, it's not like a single piece of silicon, but it's tiles and chiplets that are on top of a substrate, and the Apple M1 is a great example of that, and others are coming, and that's the future. That feels right, and I'm glad that Intel has taken a leadership position there.
He's saying by 2030, 1 trillion transistors in a chip. Pretty exciting stuff.
Yeah, so that kind of exposes what happened to Moore's Law, what happened to the end of Moore's Law. So I think what's happening is that Moore's Law talked about chip density according to a square inch, square millimeter, whatever, but it's the surface area. But now with 3D packaging and 2.5D packaging and all that, you can actually start stacking transistors on top of each other, and you're starting to build skyscrapers out of them. So it's still per square millimeter is a lot more chips, but it's more transistor budget than transistor density on a flat surface. So really what that means is speed is now via transistor budget versus frequency. And the transistor budget allows you to bring things together on a package, to use the same verbiage, than you did before. So you don't have to go off chip. And using the analogy we used last time around, you never have to leave town. The whole town is just within one, quote, chip. So that's really the insight there.
The industry, the field has become so competitive. It's a great example of why and how competition can be such a good thing for furthering innovation and technology. But Shane, with this expanded notion of system on package and these stacked chiplets becoming highly functional, what are the implications? Are there implications for the actual systems OEMs?
I think it's huge because, as the Apple MacBook Air shows, when your entire system is on a chip, not a whole lot is really outside of the chip. You have the screen, you have the keyboard, you have the power supply, and what else? I mean, that was Moore's Law, is that with every iteration, the chip would stand up, look around itself, identify some circuitry that was now eligible to be brought on chip, and it would do that. And that had huge impact on memory controllers. They now had to kind of get on chip. Floating point, units, they now are on chip. Increasingly with these tiles, you can have the GPU and the CPU on the same real estate. So that it has kind of a ripple effect across the industry, where the value add that comes from others downstream have to be different. You're no longer really adding value by assembling many chips together. You're adding value by assembling different tiles together. And if you can't do that because that's coming from the chip vendors too, so now you have to add value elsewhere. Now, traditionally, we've seen people go from systems to clusters to racks to entire supercomputers to, so that's also another dimension of all of this. And then while all of this is happening, you have architectural innovation because transistor budget lets you do that. So now you have to customize things in a different way, and composability comes into picture. So I think we are really in for fertile ground for innovation at system and cluster level in the coming years.
Helping to tie together all these chiplets and stacking its packaging. It's the Universal Chiplet Interconnect Express, UCIe, which I guess is based on the PCIe technology. That was a feature of Gelsinger's address.
Definitely. So UCIe is a really big deal. This is another level of interconnect like we talked about last time. Basically the highway system in town. And if you get out of town, then you got to do PCIe. And if you're staying within a building, then you have the CPU interconnect that exists there. So this is going to be another ecosystem. UCIe, I think, is going to be more and more prominent as time goes by. There will be pressure on all chip vendors to support it because their chips have a shot at being a tile in somebody else's package. And therefore, it's a really significant standard in my mind.
Yeah. Just to finish up with Intel, they also talked about Ponte Vecchio, their long-awaited GPU. And according to Intel's own internal benchmarks, they're putting it at 52 teraflops, which is ahead of AMD's MI250X, which is at 48. And although lagging what's expected to be coming from NVIDIA, this H100 GPU at 60.
The Hopper.
Yeah, and of course, Ponte Vecchio recalls to mind Aurora. It's going to help power the exascale system, slated to be delivered to Argonne National Lab by the end of the year. So we'll be keeping an eye out for that.
We certainly are. There was no update on Aurora at this conference. So we are due for one, and especially with SC22 coming, that's going to be a big question in everybody's mind. The hot chips, if I can go through the general agenda, they had tutorials on Sunday. They had a half a day on CXL, so it was really good to deep dive. And by the way, you can go to hotchips.org and even now register for the event and look at the video streams and download all the material. The material eventually becomes public after a few months of being exclusive to the registrants. So there was a tutorial on CXL. There was another tutorial on MLIR, multi-level intermediate representation, a way of trying to achieve better code in compiler technology using some AI tools and such. And then the conference had some academic papers from folks like Stanford, Yale, ETH. There was one from ARM that also was qualified like that. Then GPUs, AMD, NVIDIA, Intel Ponte Vecchio. There were other AI chips that had a different category. There's a Chinese company called Beren that had a really interesting chip that they talked about as a GPU. Then they talked about integration technologies, and that included interconnects. Lightmatter talked about silicon photonics. There were several other companies, Samsung, MCP, Ranovis, if I'm pronouncing their name right. And then on day two, they talked about ADAS. This is the automated driver assistance systems in cars, and it goes usually with autonomous vehicles. And then they had mobile and edge, where Intel had Meteor Lake, and then MediaTek talked about their mobile chip. AMD had some things to talk about. Intel had another talk on that. And then networks and switches, Juniper, AMD, NVSwitch were all covered. Machine learning, now this is where it was decidedly more AI-oriented rather than GPU-oriented. So Cerebras had an excellent talk, really enjoyed that one. And then there were a talk from Tesla talking about their chip and their Dojo system, a very sensible approach, but a little bit different. And of course, rolling their own is going to be a bit risky. And then a company called Untether talked about their inference chip. And then Grok talked about their inference chip. One of them is more like inference for the device in case of Untether. and the other one is more like inference at the data center. Both of them are very valid markets. And then lots of posters from different academic and companies. So really a good conference, a lot of focus on the technology and the academics. Occasionally you see some marketing activity that may be crossing the line, but generally a very solid conference.
Yeah, yeah. And I guess the one thing I would add is NVIDIA gave a presentation on their Grace Hopper chip, which combines the ARM CPU plus their GPU, which is their new high end chip
That's right. And it is their first CPU play,
with ARM, right?
which you can imagine if the ARM acquisition had gone forward, it would have been more of an in house thing. But it is also a very formidable chip. Now, they have announced that before. I think NVIDIA exemplifies the idea of announcing the same thing 4 times, like
Sure.
announcing that you will announce it, and then you announce that you are going to do it, but not fully, and then you announce a little bit more, and then you say, we just announced that we announced it.
And then you announce GA,
And
general
then,
availability. Don't forget that one.
and
So,
by then you can announce the follow-on product.
yeah. Okay.
Yeah.
Then moving over to quantum, there was a couple of developments this week. One that I covered was researchers at Los Alamos National Lab put out a paper in which they're claiming they've pretty major breakthrough on quantum machine learning, in which model training can be done with much smaller amounts of data. Now, this is a huge bugaboo for machine learning in general, how much data is required for the training aspect. But within the context of quantum, it sounds pretty impressive.
Yeah, the paper itself is pretty hard to, it's not very accessible. It's pretty technical and deep in the topic. And they certainly are focused on quantum machine learning. Now, one thing about quantum computing is that quantum computing today is not for large bodies of data. Certainly, if you're using a quantum simulator, you can use large bodies of data because the part that is difficult is to put the data into the quantum computer. And in a simulator or an emulator, that's just done in software and you're done with it. But in practice, actually putting the data into a quantum computer is complicated and time consuming. And you certainly are not going to put billions of pieces of data in there. So taking advantage of machine learning with less data is really a very significant advance in that world. So very important paper in my mind. A bigger picture of that is whether that same pattern works for classical machine learning.
Yeah.
Is it possible to do classical machine learning with less data?
Yes. And we know there's work being done in that area and has been for several years. But yeah, that's a really interesting point you're making.
Folks like Andrew Wynn have been pushing this idea of a data-centric AI, which is a focus on better quality of data such that you don't need much of it and you don't have to iterate as much. That better quality data leads to more accurate models faster, which is true. But this is talking about less data in general. And I think one of the big surprises of deep learning was that you needed a lot more data than you thought you did. Like 100,000 pictures of a cat were not enough for the system to learn what a cat is. And you could make those pictures higher quality, but you still are going to need millions of pictures, whereas like a human can learn what a cat is with a lot less info. So you would think that there is information content that is being fed to the machine that's not being absorbed. That if we find a way to actually extract more information from the data that we do have available to machines, that seems like a really, really important advance.
Yeah. There was another quantum announcement this week that you picked up on, I think, Shaheen.
It was actually a few weeks ago, and this is researchers at NTT in Japan and Princeton University basically identifying a whole new class of problems that lend themselves to quantum computing and quantum advantage. Also a highly technical, difficult to read paper. This one is about unstructured NP-complete problems, but it is nevertheless expands the universe of algorithms that are eligible to take advantage of quantum computing. So that also is a very significant scientific advance. Now, quantum computing is still in its infancy. It continues to be overhyped and underestimated, as people say, and that has to be kept in mind. However, the progress is real and is happening.
Yeah, the way I look at it, it's sort of a gigantic, very difficult jigsaw puzzle. And little pieces of it, little corners of the puzzle seem to be coming together piece by piece, bit by bit. And we'll see where we are in 5 or 10 years,
Yeah, exactly. We do see a lot of progress, but it is at really low levels of the technology. So we haven't reached our transistor moment, so to say, when we say, here's the way, here's the horse to bet on.
Here's the key.
Yeah. And even within the transistor technology, we are like building basic gates. It's like, oh, look, I did a NAND gate. Now, you can use an AND gate to build an adder, so you can add two numbers. But it's at that level. It's like when the data that you put in is still measured in voltages and things, is far from A equals B plus C. We haven't quite got there yet from a hardware level. They exist. You can now have the noisy intermediate quantum, the NISQ period that we're in. So you've got on the order of, let's say, 100 qubits. But then there's also quantum error correction that you need. There is the control systems and the input-output system that you need. So we're still ways off from a real computer, but what is there is really quite impressive.
Yeah. Now, our final topic today is another massive project, if you will, not on the scale of quantum computing, but the multi-year effort that went into the delivery installation of the Frontier Exascale system at Oak Ridge National Lab. And last week I went to the ribbon cutting ceremony. And within one room were these very senior DOE and obviously Oak Ridge. The event was hosted by Thomas Zachariah, the outgoing director of Oak Ridge National Lab. But also there was Lisa Su of AMD and Antonio Neri of HPE. So it really exemplified this massive scale of cooperation that brought together private and public sector organizations working together and delivering on time and on schedule this system. And there was a lot of pride in that room, and I think justified pride.
Absolutely. What an achievement. Also indicative that these big companies, AMD, HPE, had to make it a real top priority for this to happen. So it just shows how difficult that is.
Yeah.
And also reinforces my view that we got to get to a point where we can do these really easily. So the more we do it, the better we get. And I'm happy that we're getting the practice.
Well, on that line, I introduced myself to Lisa Su before the event, chatted with her briefly.
Oh, cool.
Yeah. And she said, well, I'm here. I take what's going on today very personally. Mm-hmm. And during her remarks, she said, we're a company of 25,000 people at AMD, but there was no higher priority project. It pulled in so many people from the company. And she said, we take it personally for our company and the country.
Right on.
Yeah, it was great.
Well, absolute, applause for all involved. This is such a moment of pride for everybody.
Yep, it was great to be there. So, well, Shaheen, great to be with you again. Thanks so much, and I'll look forward to our next talk.
All right, take care. Thank you.
Bye-bye.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The At HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.